1.3 The concept and application of sampling distributions. 1.3.1 The concept of sampling distributions. Sample is a subset of a population selected randomly or purposely for accomplishing certain objective or objectives, including conducting research, auditing financial documents, and making medical diagnosis for patients, assuring quality for purchasing goods and services, etc. Sampling distribution means the probability distribution of sample means. The sampling distribution of sample mean, X, can be used to provide probability information about the difference between the sample mean and the population mean. Example: the probability that a sample mean from 50 sample medical doctors can predict a certain characteristics of the population of 500 medical doctors in a given comprehensive specialized hospital. For instance, from a population of n equals to 5 elements, namely A, B, C, D, and E, one could select various sample sizes involving 3 elements with replacement. There are 10 alternatives of taking a sample with 3 elements, as shown below. This list of possible samples is known as sampling distributions. A sample size of n equals 4 can also be selected in this way. If a population is finite and small in number, it can be easily studied at low cost, short time duration, and little effort. That is, data can be collected from each element of the population using census, complete consideration, and generalize about the population from the result of the data collected from each element. Whereas, if a population is finite but large or infinite by nature, it would be impossible to gather data from each element of the population. Instead, a representative sample should be selected from the desired population using a suitable sampling technique. Collect data from the sample. Analyze the data gathered from the sample, and finally generalize or conclude about the characteristics of the population based on the analysis result of the sample. For instance, we can estimate population mean based on sample mean. We can estimate population standard deviation based on sample standard deviation. We can estimate population proportion based on sample proportion. Assume someone wants to estimate the population mean by using sample mean. The problem here is that the sample mean cannot exactly estimate the true population mean. An error in estimation may occur. However, the level of error may be acceptable or unacceptable. That is, if the difference between the sample mean calculated from a sample size n and the true population mean may be very small or very big. Considering the occurrence of error as a result of using sample, when the difference is small or insignificant, it can be ignored and the sample mean may be taken as a good estimator of the true population mean. For instance, to estimate the mean annual salary of 2,500 engineers of XYZ Corporation, a researcher from XYZ Corporation took a random sample of 30 engineers in order to estimate the true population mean of the mean annual salary of 2,500 engineers. After studying the annual salary of the 30 engineers, the researcher found that the mean annual salary of the sample was $51,814 with a sample standard deviation of $3,348. Now, we expect a difference between this sample mean and the true population mean. But the issue is about the extent or magnitude of the difference between the sample mean and the true population mean. One critical question can be raised here. What is the probability that the sample mean will be within plus or minus $200 of the true population mean? Suppose a researcher wants to accept the sample mean if the probability that the difference between the sample mean and the unknown population mean will be within plus or minus $200 is high. This means the researcher decided that the gap is very small and the sample mean can be a good estimator for the true population mean. Otherwise, if the probability is very small, it is required to increase sample size in order to increase the estimation accuracy or precision capability of sample mean for population mean. Especially if skewness is expected, the central limit theorem helps to improve our decision. This is because increasing sample size decreases the standard error of estimation. Then after, a point estimate or interval estimate can be implemented. An illustrative example is presented below. The data below is about the score of a student for 5 subjects. From this table, we understand that we have 10 possible random samples of size 3 from the population of 5 courses, namely ABC, ABD, ABE, BCD, BCE, BDE, ACE, ADE, CDE, and ACD with their respective sample values. Each possible sample has its own sample mean. For instance, sample ABC has sample values of 55, 60, and 72, and its sample mean is the summation of 55 plus 60 plus 72, which equals to 187 divided to 3 is equal to 62.3. We have to pay attention the sample mean for each of the 10 samples is different. But the mean of the sample means x double bar, which is also known as expected value, is equal to the population mean. That is, the mean of sample means is equal to the summation of the 10 sample means divided by the sample size. Therefore, 680 over 10 equals 68. Similarly, the population mean of the 5 elements is also 68. The standard error of estimate. The standard error is the standard difference among each of the 10 sample means. It is calculated as the population standard deviation sigma over square root of sample size. But when the ratio of sample size over population size is greater than 5%, that is when sample size is greater than 5% of population size, a finite population correction factor is needed in order to adjust a somewhat exaggerated standard error result. The finite correction factor is equal to under radical population size minus sample size over population size minus 1. In our case, 3 over 5 is equal to 0.6, which is greater than 0.05. Therefore, standard error of sample mean noted as sigma x bar is equal to population standard deviation over square root of sample size multiplied by square root of population size minus sample size over population size minus 1. The final result is 4.23. In case where population size is unknown, infinite, as well as known, but sample size is less than or equal to 5%, standard error of sample mean sigma x bar is equal to population standard deviation sigma over square root of sample size. We do not need finite population factor. Sampling distribution of sample mean. In a real world, calculating parameters of populations is usually impossible because populations are very large. Rather than investigating the whole population, we take a sample, calculate a statistic related to the parameter of interest, and make an inference. The sampling distribution of the statistic is the tool that tells us how close is the statistic to the parameter. For instance, how close is a sample mean to a population mean? How close a sample proportion is to a population proportion? Assume in the previous example of n equals 5 elements, we do not know the population mean, that is 68. So, we want to estimate it using a sample of 3 elements selected from it. Now, the question is if we randomly select any sample of size 3 from the 10 possible samples, what is the probability that the sample mean will be within plus or minus 5 of the true population mean? This is to say that what is the probability that the sample mean will be between either less than by 5 or greater than by 5 from the true population mean? For instance, we want to accept the sample mean as an estimator of the population mean if the probability of falling within plus or minus 5 is very high. Therefore, we test its probability using the standard normal distribution formula, or z-score. Z is equal to sample mean minus population mean over standard error. Now we have 2 z values for the 2 types of differences between sample mean and population mean. That is -5 and +5. Therefore, if the difference is -5, z is equal to -1.1820. On the other hand, if the difference is +5, z is equal to +1.1820. Leaving the 2 digits in the end, taking only the 2 primary decimal digits is enough. So, z equal plus 0.18 and -0.18. In the normal distribution table, the z value of +0.18 and -0.18 is equal because according to the normal distribution assumption, if a dataset is normally distributed, the measures of central tendency, such as mean and median, equally divides the data to the left, and to the right side of the bell-shaped curve. In other words, if a dataset is normally distributed, approximately 50% of the data lies to the left side, and the other 50% lies to the right side of the normal distribution curve. Therefore, in our case, z of negative 0.18 equals z of positive 0.18. The negative psi has no effect in calculation. It only indicates direction, which means the value negative 5 is found 0.18 far away to the left side from the mean, and the value positive 5 is found 0.18 far away to the right side from the mean. Z value of negative 0.18 is equal to Z value of positive 0.18. Therefore, the Z value of 0.18 in the normal distribution table is 0.3810. When this value is multiplied by 2, will be 0.7620. Assume n is very large and mu is unknown. When a sample of 3 elements is taken to estimate the unknown population mean, the probability that the sample mean will be within -5 and +5 of the true population mean is 0.7620. So, it can be taken as good estimator of the true population mean, which is 68. Otherwise, increasing our sample size improves the accuracy of estimation. Additional examples and some exercises are presented below. Go through over it for further understanding of the concept and application of sampling distribution of sample mean on making the decision of either accepting or rejecting the statistic as an estimator for the parameter of interest. Sampling distribution of sample proportion p-hat. First of all, let's see about what population proportion is. Population proportion. The concept of population proportion is the same as that of relative frequency. The population proportion is the ratio of the number of elements possessing a certain characteristic to the total number of elements in the population. When this ratio is calculated for a sample, it is referred to as the sample proportion. Assume that in a football game between Arsenal and Manchester United, 0.60 or 60% prefer to support Manchester United. If a random sample of 10 spectators were selected, it is unlikely that exactly 60% of them, or 6, would prefer to support Manchester United. By chance, the proportion in the sample supporting Manchester United could easily be a little lower than 0.60 or a little higher than 0.60. This kind of gap between a population parameter and a sample statistic is natural. but attention should be given to the magnitude of the difference between them. Because if the difference is higher, the probability that the statistic can estimate the unknown population parameter will be too low. The sampling distribution of p-hat is the distribution that would result if you repeatedly sample 10 spectators and determine the sample proportion that favored Manchester United. Population proportion noted as capital letter P equals capital letter X over population size, where X is the number of elements in the population possessing the characteristic of interest. N is the total number of elements in the population. Sample proportion, or p-hat, equals small letter x over sample size. Small letter x is the number of elements in the sample possessing the characteristic of interest. Small letter n is the total number of elements in the sample. The mean of sample proportion is the same as the population proportion. The standard error of sample proportion, which is noted as sigma p-hat, is equal to square root of p times q over n, where p is equal to the number of successes in a population and q is equal to the number of failures in the population. The value of q is equal to 1 minus p. Example: there is a population of n equals 5 graduate students, namely A, B, C, D, and E, who applied for a vacant job in their profession. 3 of them, namely Mr. A, D, and E, scored pass mark in the employment exam. Now, the population proportion, that means the proportion of students who got pass mark from the total 5 students, is 3 over 5, which equals to 0.6 or 60%. This table shows many things. 1. The population proportion is equal to the mean of the sample proportion. 2. The proportion of students who got pass mark, referred to as P, that is the number of successes. If P is 0.6, then the value of Q is the number of students who did not got pass mark. So, Q equals 0.4. 3. The standard error of proportion is equal to 0.28. Some illustrative examples and exercises are here. The concept and application of sampling distribution of sample proportion is the same as that of the sampling distribution of mean. Therefore, it would be better to pay attention on the examples and exercise the question presented subsequent to the examples.